In 6.1, we're going to start talking about what's called the standard normal distribution and just normal distributions in general. When we think about the normal distribution, we've actually already mentioned this term in previous chapters. We think of this bell-shaped curve, which when you cut it down the center, you have basically the same picture on both sides. It doesn't have to be perfect, but it's pretty close to perfect on both sides. And what that means is 50% of your data is on the left, and the other 50% of your data is on the right. So we've got half on the left and half on the right. And we've talked about this before, and it also means that your mean, median, and mode are all sitting right at the center, in the middle. And notice what we're going to be looking at when we look at using the standard normal curve, this bell curve, is that it is symmetric, meaning it's got the same picture on both sides, but it's also our first time at looking at something that is continuous, not discrete. When we were dealing with the binomial distribution, we just had a finite number of options. Somebody had one sibling or two siblings or three or four or five or six. It stopped at some point or none, but it stopped. Notice with the normal distribution curves, there are infinitely many options around in here. There's an option down here for 5.71. There's an option right there for 5.7555555555. Anything you can possibly think of that's a real number in here will fit. That is the big difference, is because this is a curve, not a bar graph. It keeps on going forever as well. So this picture we're going to use a lot in this class. It is the most important picture, I would say, in all of statistics. This continuous probability distribution is called the normal distribution. And when we look at the picture, we tend to call this picture a normal curve. And when we start talking about different values, we're actually going to look at what are called the normal probability distribution, meaning we're going to be looking at probabilities again. So you want to start thinking about, what do you know about probabilities? Probabilities always have to be between 0 to 1. If you have all your probabilities and add them up, they should add up to 1. And what we're going to see with these normal curves and the standard normal distribution is that these areas that we're going to see on our pictures are going to be equal to the same thing as being asked to find a probability. So whether or not you're asked to find an area or a probability, it won't matter. They'll be the same thing. So we know that if you were told to add up all your probabilities, they'd have to add up to 1. So if that means the same thing for the area, because they're the same, it means if you add up all the areas, they should also be adding up to 1, because areas are going to be treated just the same way as probabilities. And we said that the mean, median, and mode all end up right smack dab in the middle, and that's because they are all equal. The mean, median, and mode are all the same, and they're all equal. What did we say else about the graph? Is it has the same picture on both sides, which means it's symmetric. And it has this shape, and I know I'm not the greatest artist, but this will be close enough. It's this shape, and it's called a bell shape. And what always goes in the middle? We've been doing this for a while. What goes in the middle is the mu, the mean. And what do we notice about our graph? We've kind of used this without saying it, is that on the ends of our graph here, as we get closer and closer and closer to the x-axis, but we never actually are going to touch the x-axis. And there's a special name for that in math courses. It's called an asymptote. when you get closer and closer and closer but never actually touch, is that what that means is our graphs are going to go on forever. So there are a lot of different normal distributions. They all look the same, kind of. Some are skinnier, some are fatter, and some are flatter. So if you look at these next few, notice they all look a little bit different, but they're all bell-shaped, they're all symmetric, and it's just whether or not they're taller, skinnier, that sort of thing. So the question is, what makes one taller, skinnier, thinner, flatter, that sort of thing? Well, remember, we've done these kind of graphs before, and how we created them, our bell curves, was we inputted our mean. Our mean which was determined our center value. And then how far out we go on either end was determined by adding 2 standard deviations or subtracting 2 standard deviations from the mean. So what's going to make me taller, fatter, wider, moved left or right is all going to have to do with 2 things. Your mean and how far out you're going to get pulled in either direction is going to be based on your standard deviations. So if I look at all 3 of these curves, let's see which one's actually going to be basically having different standard deviations. Well, let's take a look at a couple examples first, and then we'll come back to these pictures. So we'll come back to these 3 pictures in just a second. How I want to kind of illustrate this is look at these first 2 on the same picture. So I'm going to draw a number line, and I'm going to draw the numbers 5, and the second graph has standard deviation of 2, and the first has a half. So I'm going to go actually units of 2, just to kind of illustrate. So we'll go up 7 and 9, and on the bottom we'll go 3 and 1. So I'm actually going to draw my bell curve for my second graph first, because what this means is if my standard deviation is 2, remember that most of my data should always be within 2 standard deviations, which would be that 9 and the 1, because adding 2 standard deviations, well, adding 1 would be 7, adding 2 would be 9, subtracting 1 standard deviation would give me 3, subtracting 2 would actually give me all the way out to 1, where my mean, which is 5, is here in the middle. So what I would do is to draw my bell curve appropriately is the majority of my bell curve should be in between the 1 and the 9, because that's 2 standard deviations within my mean. Now, if I want to draw my first problem here on the same curve, that's this one here, it's going to have the same mean at 5, meaning the center should still be at 5, but my standard deviation should be a half this time. Means it's not going to go out as far, but it still has to have the same area. It still has to have an area that adds up to 1. So if it's not going to go out as quite as far, okay, but then it's still going to have the same area, means if it doesn't go out as far, it's going to shoot up to cover up that area. So a standard deviation of a half means if I go out 2 standard deviations, going out 2 standard deviations and to the right would actually mean going out 1 unit, because a half twice would be going out 1, which means I'd go out here to 6 on one side, and then going out 2 standard deviations on the other end would mean I'd go out to 4, and then the majority of my picture should be crammed into that area with the same area though. So it's going to end up being taller this time. Same shape, just taller, because it's the same amount of stuff just shoved into a tighter picture. And then that is my graph for number 1, is that tighter, higher graph, because all my data should be between 4 and 6, or at least the majority of it, because that's 2 standard deviations on either side of my mean, 5. So This gives you a good idea that the mean tells you where the center of the graph is, whether you're to the left or to the right, but the standard deviations tell you how far out you're going to be pushed. If your standard deviations are bigger, it means it pushes your graph down a little bit. It squishes it down. But if your standard deviations are smaller, it pulls up your graph because you've got to fit more area in a tighter spot. So if we go back to our 3 graphs at the top when we were talking about which one has the smallest standard deviation first. Well, which one has the smallest standard deviation is actually going to be the one that ends up being the tallest because you've got to push more area into a tighter space. So the one with the smallest standard deviation is actually going to be the tallest one down here. This one has the smallest standard deviation because I've got to stick more stuff in a tighter spot. Okay, what about the one with the largest standard deviation then? Well, the largest should then, by comparison, be the shortest and flattest one, which should be the one in the middle, because then you have more space to fit your graph in. So this one's going to be the largest standard deviation. Notice these are all normal curves. They're all bell-shaped, they're all symmetric, they all go on forever. But so what happened is people got really tired of, oh my goodness, there are so many different kinds of normal curves. They all look very similar. They're all bell-shaped, they're all symmetric, they're all slightly different. And people